Hey everyone, welcome back. Today we're tackling a really interesting problem called smallest missing non-negative integer after operations. It sounds a bit complicated, but we're going to break it down step by step and see that it's built on one very clever idea. Let's get started. Okay, so the problem gives us a list of numbers, called nums, and a single integer called value. We can perform an operation on any number in our list. We can add or subtract value from it as many times as we want. Our goal is to perform these operations to get the highest possible max. First, let's make sure we understand this term, max. It stands for minimum excluded value. All it means is, what's the smallest non-negative integer, so 0, 1, 2, and so on, that is missing from our list. For example, if we have 1, 0, and 3, we have 0, we have 1, but we don't have 2, so 2 is our max. If our list is minus 1, 2, and 3, we start checking at 0. And since 0 isn't there, the max is 0 right away. Now, let's think about the operation. We can add or subtract value over and over. This is the key to the whole problem. Let's say we have the number 7, and our value is 5. We can subtract 5 to get 2. We can add 5 to get 12. All these numbers we can create. 2, 7, 12. They all share something in common. If you divide any of them by 5, you get the same remainder. 2. And that is the aha moment. The operation basically lets us swap any number for another number, as long as they belong to the same remainder family. This changes everything. The problem isn't really about the specific numbers like 1, -10, or 7. It's about how many numbers we have available for each possible remainder. So with that insight, how do we find the maximum possible max? Well, a high max means we've successfully created a long chain of numbers starting from 0. Like 0, 1, 2, 3, and so on. So let's just try to build that chain greedily. First, can we make the number 0? To do that, we need to have a number in our input whose remainder is 0. If we do, great, we use it. Now can we make one? We check if we have any numbers with a remainder of 1. We keep going like this until we try to make a number, say k, and find we have no numbers left with the right remainder. That means k is the smallest number we can't make. And that's our max. Let's walk through the first example to make this solid. We have our list of numbers and a value of 5. First step, let's find the remainder for every number and count them up. 1 gives a remainder of 1, -10 gives a remainder of 0, 7 gives 2, and so on. After counting, we see we have 1 number for remainder of 0, 2 numbers for remainder of 1, 1 for remainder of 2, 2 for remainder of 3, and 0 for remainder of 4. Now let's use these counts to build our sequence. Can we make 0? Well, 0 modulo 5 is 0. We look at our count for remainder 0. It's 1. Perfect. We can make it. We'll use that number up, so the count for remainder 0 becomes 0. Next, can we make 1? 1 modulo 5 is 1. We have 2 numbers for remainder 1. Great, let's use one of them. The count becomes 1. We can make 2, and we can make 3. Now, can we make 4? 4 modulo 5 is 4. We check our counts for remainder 4, and it's 0. We have no numbers we can use. We're stuck. So 4 is the smallest number we couldn't make, which means 4 is our answer. Just a quick heads up, we'll be walking through the solution using Python, but don't worry if that's not your main language. The logic is exactly the same, and I'll be showing the full code for other popular languages like Java, C++, and JavaScript towards the end of the video. Alright, here's the Python code for this greedy approach. As you can see, it's very short because the logic is so direct. Let's break down the 2 main parts. The first line is where we count up all the remainders. This is a neat Python feature called a generator expression inside a counter. It goes through every number in our input list, calculates its remainder when divided by the value, and the counter automatically keeps track of how many times it sees each remainder. So after this line, our map, called MP, holds all the counts we need. Next, we have the core greedy logic. We initialize our potential answer, max, to 0. Then the while loop starts. The condition inside the loop is the main check. It looks at our map and asks, for the remainder that our current max needs, is the count greater than 0? If it is, it means we can make this number. So we decrement the count for that remainder to show we've used 1. And then we increment max to try and build the next number in the sequence. The loop will keep running until this check fails, at which point, the current value of max is exactly the number we couldn't make, and that's our answer. So how efficient is this? For time complexity, we go through the list once to build our map, which is big O of n, where n is the number of items in the list. Then, the while loop runs. In the worst-case scenario, we could use every single number, so the loop could also run about n times. This gives us a total time complexity of big O of n. For space, our map stores the counts for each possible remainder. Since there are value possible remainders, from 0 up to value -1, the space complexity is big O of value. Alright, as promised, here is the full solution in Java. You can see the logic is identical. We create a hash map to count remainders, handling the negative numbers carefully, and then we have the same while loop to find the mex. Feel free to pause and take a closer look. Next up, here is the C++ version. We use an unordered underscore map for our frequency counter. Notice the x% value plus value % value trick. This is a common way in C++ and Java to ensure that the remainder of a negative number is always positive, which is what we need. And finally, here's the solution in JavaScript. We use a map object to store our remainder counts, but otherwise the structure is exactly the same as the others. Seeing it in different languages really helps show how the core greedy idea is the most important part. So let's wrap it up. The biggest takeaway here is how a seemingly complex operation can be simplified by looking at its mathematical properties, in this case, modulo arithmetic. Once we realized it was all about remainders, a simple and efficient greedy strategy became obvious. And this pattern of using a frequency map to count things up is a technique you'll use all the time. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the Playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems. So if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. This channel doesn't make any money from sponsorships or ads yet, so if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.